So far in this unit, we've spent a lot of time talking about the parts of a function and its graph. We've also spent a considerable amount of time talking about extrema. And when we're finding minimum and maximum values, what we're really doing is we're doing this process of optimization. Now, optimization means we are trying to minimize or maximize a situation. There's probably a lot of things that you do in your own life that you try to optimize. For example, you try to hopefully maximize the amount of things that you learn and can get done while you're at school, so you can also maximize the amount of time you have outside of school to do things like play, work, sleep, whatever it might be. And so you have a sheet, and with that sheet, at the very, very top of it is a list of items that we need to ensure that we do when we do problems dealing with optimization. And so I'd like to kind of go through those with you a little bit. And then we're going to go ahead and do a problem as well. Now there's 4 problems at the bottom there. And in this video, we're going to go ahead and tackle one, and that is problem A. So formally, we're introducing you to the process of optimization, even though we've talked about it in a previous problem that we did throughout this unit and in little bits and pieces as we learned everything we needed to get to this point. So the process. First of all, when you optimize, you have to create your own mathematical models, your own equations. And there's usually 2 equations that you'll have, sometimes just 1, sometimes 2, maybe even more than that. But what we have is we need what's known as a primary equation. Now, the primary equation is the equation that we derive to find the min or max. And we would like it to be in one variable. And in fact, we're going to do it so it is always in that one variable. Now, the secondary equation is kind of the helper equation. It's an equation, you might even think of it as a formula, that we use to plug into the primary equation so we can get the primary equation into one variable. So the first thing is we identify the models. What do the equations look like? Second of all, once we have identified the equations, we need to use the secondary equation to get the primary equation explicitly in the variable that we would like to use or solve for. So this involves taking an equation with multiple variables, solving it for one of the variables so we can substitute back into the primary. Third, when you optimize, you have to think about the domain. And by that, I mean, are negative numbers allowed? Is 0 allowed? Do we have a certain window of numbers that we need to be working in or solving within? And that comes from the context of the problem and the equations that you set up for. Once we've considered everything, we have a primary equation. Again, we would like to have it in one variable. We go ahead and derive that primary equation. After we derive the primary equation, we're going to, again, we're looking for an actual solution. So we're not dealing with, in our context, any piecewise type functions. So we're going to set the derivative equal to 0, because we know asymptotes aren't going to really help us because they're not a min or a max, but we're really looking for critical numbers. And those are going to come from setting the derivative equal to 0, those hills and valleys, okay? After we go ahead and find our possible extrema, we can verify that those possible extrema are indeed mins and maxes by finding the second derivative and using the second derivative test for extrema, as noted in step 6. Now, because we might have been working with multiple variables to finish our problem, we might have to find any other variables that are left. And that means taking that that extrema value and plugging it in for those other variables. Okay. So the problem we're going to look at is this right here, and we're going to go through the steps. Problem A in the problem set, we have 0.8 cubic centimeters of medicine is to be placed in a gelatin capsule. We want to find the radius and the overall length of the capsule such that the smallest amount of gelatin is used to create the outer shell. Now, if you think about this, in terms of medicine, we've all probably taken medicine in some kind of capsule form. And so when we create this figure, we don't want to take this, I guess, massive horse pill. I mean, yes, we've probably had to take medicine, and maybe you've taken like a pill or a vitamin that's like, holy cow, that is really, really big. And so we want it to be as small as possible, but still be able to contain the 0.8 cubic centimeters. So the capsule is going to be formed in this way. We've basically got a cylinder, and we've got two hemispheres that we've just like stuck on both ends. So imagine almost like a can, and then we cut a tennis ball in half and put one half on one side, one half on the other. Okay. So we are trying to do this. We are trying to minimize the surface area. Okay. So that's the context of the problem that we are now going to be working through. So let's go ahead and find the formulas that we need. Now, as you navigate these things, there might be some times where, I will give you a formula, but some of these formulas we have to kind of go find ourselves once in a while. Okay. But assessment-wise, yes, you'll be given the formulas that you need if I don't think it's something that you have a lot of exposure to. So here we go. First of all, we're going to need a volume formula. And that volume formula is going to be for the cylinder and basically the two hemispheres put together, which make a sphere. So volume is 4/3 pi r cubed. That's the formula for the volume of a sphere. Plus, now the volume of a cylinder is the area of the circle times the height. Okay. All right. Now, surface area. Well, the formula for the surface area of a sphere is 4 pi r squared. Now, what we need is the surface area for the cylinder. But you know what? We don't need the area of the surfaces of the top and the bottom. We only need that rectangle. See, we really only need is this part right here. Okay, these ends, okay, are going to be open. So the medicine's going to go right through this cylinder here. Okay, so we need to keep the ends open so it can go into the two hemispheres on the side. So really what we need is we need to like unroll the cylinder, and we end up with a rectangle. So that rectangle has a length and a width equal to the height and the circumference of the cylinder. So that's going to make it plus 2 pi RH. And what we're trying to do is we're trying to minimize this equation right here. And so this is our primary equation. Okay, we want to make that as small as possible. Now, the volume equation, well, our volume is given as 0.8. Now, I'm going to write 0.8 as a fraction, 4/5. And this is a secondary equation. The reason why is I really don't want to have to deal with decimals. I have to make a choice. Decimals are fractions. And I'm looking at the 4/3 there, and I'm going, hey, That is not a decimal that is going to be finite. It's going to continue to repeat. I want to work in the world of fractions. Okay, that'll make everything the most accurate. So I have my models. I have a surface area formula. I have a volume formula. I have a primary and I have a secondary. But what I need to do is I need to change the surface area formula so it either has all R's or all H's. Because there's only one H there, it's going to be a lot easier to write the surface area equation in terms of R. Notice I didn't write SA as a function yet. I just have it kind of a general statement. Okay. So let's do this. We're going to take this volume equation and we're gonna kind of take it apart if you don't mind. So what we need to do is we need to go ahead and get rid of the fractions. That would be kind of helpful. So again, we're gonna ignore this v over here on the left because that's really equal to 4/5. So again, we're working right off of here. So let's multiply everything first of all by 15, because 3 and 5 both go into 15. So that's going to give us a new formula here. And that new formula is going to be this. And then I'm going to kind of work kind of the other way. So 5 goes into 15 3 times, that's 12. Okay. And then this 3 goes into that 15 5 times. That's going to make that 20 pi r to the third. And then I'm going to add 15 pi r squared h to that. Now, if I solve for h, I'm going to have to subtract the term with the 20 in it to the left and then divide. So I'm going to end up with 12 minus 20 pi r cubed over 15 pi r squared, and that's going to be the value of h. Now, if all three of those terms, that 12, the term with the 20 in it, and the term with the 15 in it, all can be simplified, my gosh, do you want to do that right here? You don't want to work with huge things if you can help it. Okay. So now let's write a surface area equation as a function of r. So when we do this, here we go. We're going to have 4 pi r squared plus 2 pi r, and this h up above is going to become the new h, which is 12 minus 20 pi r cubed all over 15 pi r squared. Okay, now before I take any derivative, yes, I have a primary equation in one variable, but it's not real simplified yet. So let's continue on that journey and do simplifying. So 4 pi r squared, you're just going to have to be a little bit patient for a little bit here. All right, what can we do? Well, this pi and this pi will go away and become 1. This r can go away with this r squared, but it'll still leave an r left. Okay, so I can get it to there. Now, what that'll give us then is that'll give us the plus 2 still there. And now we've still got 12 minus 20 pi r cubed. And that is all over, we'll put that all in parentheses, still 15r. Okay, so it's a little better looking. So now what I want to do next is, again, patience, 4 pi r squared, we'll get to you soon, is now let's distribute not only the 2 through everything, but the 15r through both terms in parentheses too. So what that'll give us, again, we'll take some baby steps here, that'll give us 24 over 15r minus 40 pi r cubed over 15r. Okay. Now, at this point, let's clean this, let's continue to clean this up. So this is 4 pi r squared. Now this part, now I'm going to take a derivative here in a little bit. This is going to become 8/5, but I'm going to scoot that r up to the top. So it'll be r to the -1. Now 40 over 15 reduces to 8/3 pi, and r cubed over r is indeed r squared. Okay. So we're getting there. Now, take a look. If you look at the equation we have an opportunity, because you'll notice that we have an r squared on the right, and we have an r squared term here. They both include a pi also. We can actually combine those. Okay. So let's go ahead and do that. Now we have to think a little bit about fractions, don't we? So that 4 in front of the pi r squared is really 12/3, isn't it? Let me just make a note. 4 is the same as 12/3. So what I have is I have 12/3 minus 8/3. What I really have then is I have 4/3 pi r squared plus 8/5 r to the -1st. Wow, all the way down to that. Let's look back to where we started. Okay, primary and secondary equations. We wrote the volume equation in terms of H. It wasn't going to look very nice, but we were able to simplify, continue to do that, combine like terms, and here we are. And we have a simplified primary equation all the way down. Now, what if you don't see to simplify those terms? Are you still going to be okay? The answer is yes, you will. You're just fine. Okay, now let's keep going. So now we're going to take the derivative of that. Okay, so r squared is the variable. So 2 times 8 or 2 times 4/3 is going to give us 8/3 pi times r. And then using the power rule, that's going to be -8/5 r to the -2nd. All right. Now, this we can simplify. And I'm labeling everything as I go. So this is 8/3 pi times r minus 8/5 r squared. Now, I found a derivative. I don't have common denominators yet, so I need to work on that step before I can set it equal to 0. Part of it being because I have a variable in the denominator still. So what I'm going to have to do is I'm going to have to multiply this left one by 5r squared. So 5r squared over 5r squared. So I'll just show that. This by 5r squared, and this one's going to need a 3. Okay, so that's going to give us 40 and a pi and an r cubed, and we'll have the same denominator here in a second, and that'll be minus 24 over 15 r squared. Okay, so we are looking for an answer now. So we're going to set the derivative, sorry about that. We're going to set the derivative equal to 0. Okay, if we set the denominator equal to 0, we're going to get r equals 0. Well, you can't technically have a radius of 0. It's not in the domain in this case. So we solve this. Now, when we solve this, okay, we're going to add 24 to both sides. And we're going to then divide both sides by 40 pi. And then we're going to have to take the cube root of that. And this is an exact answer right here. When you put that in your calculator, you got to make sure that you put parentheses around this 40 pi. Otherwise, you're going to get something really, really different. Okay, now, here's another note. When you put that in the calculator, you're going to get an answer. And that answer is probably going to be around 0.576 centimeters. Now, if you round that off, then when you find other values, it's going to throw those other values off. So what you want to do is you want to leave that value fully intact as long as you can. So how do you do that in your calculator? Well, we've talked about it a few times, and we're going to put it into action here. And as we start working with really, really crazy decimals, this is just kind of a good skill to know. What you need to do is you need to find the button, bottom left-hand corner. It's STO, store. Okay. So as soon as you get that answer, you're going to hit store, and then you're going to hit alpha, and you're going to pick a letter. Those are usually in green on your calculator, like A. And then once you do that, you might have to hit enter. All it's going to say is the number and done. Now, what that allows you to do is it allows you to use that number anytime you hit alpha and that letter, like alpha A, and it pulls up the letter A for you. It's going to remember that. It's like a memory feature on the old calculators you might have had in elementary or middle school. Okay. So, is this our answer? Well, it's the only answer we came up with. It has to be. But how do we know it's a min? It's kind of amazing how the math works in this aspect of things. Well, let's say we went ahead and took the second derivative. Okay. So change colors here. So the second derivative. Now, if I were doing this, I would take the second derivative off of this one right here, because I don't have to use the quotient rule. It's just right there. So my second derivative would be 8/3 pi, and then that would be plus, because -2 times a negative is positive, and that'd be 16/5 r to the -3rd, or it would look like this. Now, if you take the value that we got, and I'm just going to put in 0.576 just to show you. If we put that in, what kind of answer are we going to get? Well, we're going to get a positive answer. The value of this is greater than 0. So what does that mean? It means that 0.576 we're concave up. That's what the graph looks like, which means this has to be a minimum. Okay. Now, what did I just find? Well, I just found the radius of the sphere or the cylinder, because they're the same. So what I have to do to finish this is I've got to find the height of the cylinder. Okay, back to our problem. So I know the radius. I know this distance. I know this distance. What I don't know is I don't know how long this needs to be. So let's figure that out. Okay, so here's what we do. We take this value. Remember, you've stored it. And we're going to put it all the way back into, this formula right here. And you're going to work it out and find what H truly is. And you know what happens? When we put the value of R in, we get H to be very, very tiny. In fact, now depending on the number of decimal places your calculator will do, H could be 0.001. You know what? H could be 0. Depending again, how many decimals your calculator will indeed calculate. Okay. If you have a basic calculator, you might have 0.001. If you have If you have a graphing calculator, it might give you 0, or e to the negative 12th power. It means you're moving the decimal point 12 times to the left, whatever it might be. But it is very, very small. So what do we learn? Well, we learn that to make a capsule using the smallest amount of material, that we should make it basically so the cylinder basically has little to any height at all. So you know what this actually tells us? The optimal container, or the optimal shape for a container like this, basically is a sphere. Now, that little cylinder that's in between that hardly exists is probably just enough to put the two hemispheres together. Mathematically, that's the optimal shape. Those are the optimal dimensions. The question is this: is it practical? Because we're dealing with medicine that is it's the size of a ball, a sphere. Practical. Well, two things to think about. Number one, what you'd have to consider is this: who's taking this medicine? You know, if you had a piece of candy that was like a ball, I mean, is that easy to hang on to? Probably not. That's one thing to consider. The second thing to consider is, could you take something that size and could you swallow it okay? That's another issue. Would it get lodged in your throat or somewhere else on down the way? So when you go through these optimization situations, you have to think logically about other factors that might come into play. Okay? So just because we've minimized and maximized a situation doesn't mean that's what we want to go with. It kind of gives us a baseline to what we want to do. Okay. Now, in a lot of cases, yes, the optimization process gives us exactly what we want, and we can apply that and use that. But again, when we're talking about things like this, we might have to change things up a little bit. So how do we verify this? And is it possible? Because we have a function and it's one variable. Could we graph it? And the answer is, yeah, we could. In fact, here's the graph. Here's the graph that we're seeing right here. And you'll notice what this function does, but also you'll notice this. We're not worried about the left side or the second and third quadrants, are we? We're worried about the right side. So the 0.576 is the radius. Now, what does the 4.168 represent? Well, the formula that we were working with was dealing with surface area. So this formula then gives us the surface area of the entire shape, 4.168, and that would be square centimeters. The 0.576 is just regular centimeters. So we're talking about something about a centimeter in terms of overall diameter, kind of a sphere about that size. Okay. Now the last question that was asked on this was, what's the overall length? Well, if it really truly is going to turn out to be a sphere, we can take that 0.576, the actual value in your calculator, take it times 2, and that would tell us the overall length. So we're talking about 1.152 centimeters. When you work with technologies like nanotechnologies, again, you want to be very, very precise and specific in your calculations as well. And we are really moving to those types of problems in our world today. So that is a formal introduction to optimization, the process, and then going through the steps in a situation like that. Again, we can do all the math, but we have to make a good decision about, hey, are these values going to be helpful? Are there things that we can tweak in it? Maybe we do want a cylinder there, but maybe we want it to be like twice the radius. So maybe we change H into, 2R, whatever it might be. But we can change some conditions in our models to navigate and get what we're looking for as well. So I'll be back to teach you a little bit more and to do some more work with optimization and situations of creating mathematical models to find mins and max. Thanks for watching.